Thank you for joining us today for this deeper dive into material adoption for metal additive manufacturing. My name is Mihaela Vlasea. I'm a faculty member in the Mechanical and Mechatronics Engineering Department at the University of Waterloo and the research co-director of the Multi-Scale Additive Manufacturing Lab, where I have the pleasure of working with exceptionally talented researchers on powder bed metal additive manufacturing technologies. I'm extremely enthusiastic to host this hybrid webinar and panel session showcasing efforts in laser powder bed fusion process parameter optimization for high-strength aluminum alloys as a collaborative venture between the Barnes Global Advisors, or TBGA, and the Multi-Scale Additive Manufacturing Lab, or MSAM, at the University of Waterloo. Now, both TBGA and the MSAM groups have a strong mandate for engaging with industry and disseminating knowledge to strengthen confidence in additive manufacturing technology adoption and really to provide insights in the path towards industrialization of these processes. Now, before we begin, I would like to remind everyone that this session is being recorded, and if all goes well, a link to the content will be made available shortly. Also, at the end of the event, we will be available for an extra 30 minutes to network and engage in conversation with you in the roundtable discussions. So I hope you had a chance to look and play a little bit in that environment at the beginning of the session. And really, for today's session, we have three main goals. First, we would like to highlight the motivation behind the need for new alloy development and for new material adoption for metal additive manufacturing. Secondly, we would like to showcase the range of efforts that really go behind process parameter development in laser powder bed fusion, and specifically for high reflectivity alloys, which are notoriously difficult to work with. And lastly, we would like to have an open discussion on the realities of technology adoption for industrial applications. So now to accomplish all these tasks, we have put together a series of 3 technical videos along with alternating panel discussions. So with that said, it is really my pleasure to have today on the line 3 panelists who will bring to light the need for AM material adoption for high-strength aluminum alloys, as well as highlight what it takes to go from powder to part in laser powder bed fusion. So first, and I invite John to turn his camera on if possible, we have John Barnes, the founder and managing director of the Barnes Global Advisors. John Barnes has a 25-plus-year career in product development and aerospace with Honeywell, Lockheed Martin, Skunk Works, Australia's CSIRO, and Arconic. He's been involved in metal AM throughout his career, beginning in the late 1990s, where he was part of the Sandia National Labs, the Lens Crata. Since then, he has been in and around AM, working both technical as well as business cases for implementation and development efforts, specifically in materials, powders processing, and printing. And really, John's goals have been to mature the technology for practical applications. And he's really recognized internationally for contributions in AM, in product development, and leadership in engineering. And he is a materials engineer at heart and by background, and has developed expertise in manufacturing for a very wide range of sectors. He is an adjunct professor at RMIT and Monash in Australia. And in 2014, he was actually recognized as Purdue's University Materials Engineer of the Year. And since 2017, we've been lucky to have him as the Additive Manufacturing Technical Community SME advisor. So we've benefited from his expertise, reputation, personal commitment, and volunteer time to really expand the use of additive manufacturing in the field. Our next panelist is Dr. Kevin Slattery. So I invite Dr. Slattery to turn on the camera, who is the additive manufacturing advisor and really an accomplished technology guru at the Barnes Global Advisors. Dr. Kevin Slattery was most recently the chief scientist scientist for additive manufacturing at Boeing Research and Technology, or BRT. He was responsible for developing and integrating the technical roadmaps and development plans for metal AM for the entire organization. And prior to that, he was the chief scientist for metals, ceramics, and mechanical systems at BRT. He served as the division chief engineer for USN and USAF fighters and US Army rotorcraft in Boeing's military sustainment organization, including international operators. Now, spanning 1997 to 2012, he was on the BRT Metals team as a researcher and senior manager, and he primarily developed and advanced low-cost titanium processing technologies supporting all Boeing products. And he was really the technical and programmatic lead in implementing the first aerospace metal additively manufactured structural aircraft components for both spares and production. Kevin is quite accomplished. He holds over 34 patents, lots of patents pending, and he's also a materials scientist at heart with a bachelor's and a master's degree in metallurgical engineering from Missouri-Rolla and a doctorate in materials science from Washington University in St. Louis. And last but not least, I invite Sagar to turn on his camera. Sagar Patel is a young up-and-coming PhD who works with me in the MSAM lab on the material science, process physics, and design considerations for laser powder bed fusion additive manufacturing. In the MSAM lab, we call him the AM Tech Whisperer, since he was able to work with some really unconventional aluminum, titanium, and ferrous alloys and produce high-quality parts through the use of modeling and material science insights. He has won numerous awards, including the Doctoral Thesis Completion Award, the Paul Neeson Tech Award, the Rapid Plasticity Best Poster Award, and the Rapid Plasticity Digital Manufacturing Runners-Up Award. And last but not least, the Advanced Manufacturing Olympics Award for our work with the Barnes Global Advisors on Scalmalloy. And a big thank you to all our panelists being here today, and to our TBGA and MSAM media helpers in the background. Now, one of the opportunities to really springboard laser powder bed fusion industrialization and technology adoption is to increase the materials that can be processed with high quality and reliability. And such is the case for high-strength aluminum alloys. So now let's take a quick look at a short clip describing this need. Let's play the video.
The aviation sector previously used additively manufactured Ti-6-4 to substitute for conventional high-strength aluminum alloys. This is because conventional high-strength aluminum alloys are susceptible to cracks during additive manufacturing. Groups such as the United States Air Force are hence interested to test the advances in aluminum materials and additive manufacturing processes to produce high-strength sustainment parts. Aerospace and defense applications in particular will benefit from having an additively manufactured high-strength aluminum alloy in several ways. First, the higher mechanical properties will benefit sustainment by providing an AM alternative for the replacement of more highly loaded parts originally made from 200, 300, 2000, 6000, and 7000 series alloys. Secondly, a high-strength alloy with simple post-processing will enable more optimized future designs without the complications of solution annealing and quenching that can result in residual stresses and distortion. Finally, a high-strength alloy with broad industrial use and multiple powder suppliers will ensure both availability of powder and a competitive pricing environment, especially as demand grows and additional sources of alloying elements become available. Our group chose to investigate Scalmalloy as it is the most mature, high-strength aluminum alloy available that is not susceptible to cracks during manufacturing. The Toyal group supplied the sample of Scalmalloy, which were ultraspherical powders with low oxygen content that is beneficial for all metal additive manufacturing technologies. This material was a good option for our group to demonstrate process parameter optimization in laser powder bed fusion. Laser powder bed fusion provides unique design freedoms and opportunities for structural lightweighting. We set an ambitious goal of going from powder to maximum density parts with good surface quality in less than 2 weeks. This is an ambitious goal for laser powder bed fusion process parameter development, where the optimization cycle may take months.
Now, stemming from this video, and we'll probably reenact some of the content there through the discussion with the panelists, I'd like to ask our panelists a few questions to move the conversation further. And I do encourage the audience members throughout the session to type up questions in the chat, and we will do our best to address them, either now or at the end of the session. My first question is for John. So John, what are the market sectors that you think could benefit from the use of high-strength aluminum alloys?
Well, of course, aerospace is the predominant user of the high-strength materials. As the video mentioned, the 2000 series and the 7000 series were developed specifically for different applications, in and around the fuselage. And so aluminum enjoys a good specific strength, but also a good specific stiffness. And, I think this is the unsung hero of material science, is that stiffness is usually more important than strength, but it's nice to have the strength. Where we've gotten to recently, though, and especially with additive, is looking in applications like heat exchangers, where the unique properties of Scalmalloy can come in, where you do require high strength. You can thin out the walls of the heat exchangers, thus improving their heat exchange, properties. You take advantage of the strength that way, and you get more surface area, thus allowing the performance of the heat exchanger to improve. So I think that's some of the more novel uses of these materials. And aluminum has very good thermal conductivity. It's another thing that's not widely used, and because we think about strength a lot of the times. So I think anywhere where 7000 series, is used, it doesn't quite approach the strength of 7000 series, but certainly better than the aluminum silicon 10. And the material science is important because to get the 7000 series, and to some extent 6000 and the 2000, they're not considered to be weldable materials. So it's a bit of a struggle in a fusion-based process. We do things to make it work, but Scalmalloy being weldable actually doesn't require additional attention. Let's say it's printable right off the bat. So I think there's a lot of interesting things with Scalmalloy. Scandium additions has long been an interest to me. It's a little known element to people out there, but does very interesting things in small quantities to aluminum.
Now, you kind of hinted a little bit to this, but in your personal opinion, where do you think AM would contribute specifically for these alloys in terms of potential through design? So specifically in using aluminum alloys, what do you think are some of the target applications that you think may be emerging or springboarded by the use of AM in combination with high-strength aluminum alloys?
Yeah, I think it kind of makes it more so. I think the ununderstood thing or misunderstood thing about aluminum is in AM specifically is that everybody thinks that it's the same thing as why we do tie and nickel, except it isn't. The value proposition is very, very different. Aluminum is much more affordable material. It's not a premium material like titanium and nickel. It machines much more easily and quickly than titanium and nickel alloys do. So the commercial side of it is vastly different. And so you really have to be good at your design, your DFAM capabilities to extract the value in using a high strength aluminum. And when you get a high strength aluminum, then you're into a slightly higher, let's say, price material, but then it moves it back more towards like a titanium and a nickel in terms of you have to have this design element there, and really look at consolidating parts. As we talk about in our maturity model with TBGA, we look at level 2 parts, which are sort of part for part comparison. That's not a great place to be. For these types of materials, they have to move where you're consolidating parts and or adding functionality that didn't exist before, like the heat exchanger, where you can get significantly better performance out of that. But you got to basically start with a clean sheet.
So kind of along the same line, so moving from the design to the material level, my next few questions are for Kevin. So when you're comparing, for instance, conventional manufacturing approaches for high-strength aluminum alloys and additive manufacturing, first of all, what are the traditional manufacturing processes for these alloys? And furthermore, for AM, what are the added advantages that you think at the material level or perhaps functionality level we are adding to by processing these materials via laser-based AM?
So with the exception of a few of the aluminum alloys, aluminum silver alloys 200 through 206, all the high strength aluminum alloys are made by wrought processing. That's either sheet and plate, which comes off a rolling mill and is a simple rectilinear or flat shape. Extrusions, which get pushed through a press, which can be a 2D shape, but it's just a 2D shape. You have to form it. You have die forgings, which can give you a bit of 3D shape, except of course the die you always have to be able to get the die apart. And forged block, which is just a rectilinear shape or simple shape or ring or something like that. The way aircrafts were originally made out of aluminum was it was all sheet metal, it was all extrusion and lots of rivets. We saw even in a very, very large aircraft like the wing spars of very large aircraft were originally made out of sheet metal or thin plate and extrusions that were fastened together. Later on, smaller aircraft moved to forgings to do that. And in the early to mid 90s, there was really a revolution in aircraft manufacturing, which was due to high-speed machining and high-quality thick plate. You couldn't before the late 70s, early 80s, you couldn't really get, if you got plate thicker than 100 millimeters, you started to have a real knockdown on properties. The aluminum mills not only improve their processes, but they also improve their alloys to get there. And now you can get plate probably up to 300 millimeters thick that retains very good properties. That also opened up the first door to really go with high-speed machining to do, I will call it 2D unitization. So you're able to take something that was built up from a bunch of sheet metal parts, took lots of tooling, to now buying a solid block or solid piece of plate and machining it all at once. Did wonders for tolerances. Actually, even though you're turning 99% of the material into chips, it was still cost savings because aluminum is cheap and labor to rivet is expensive, even with automated riveting. But you hit a law of diminishing returns there. Once you start to get above, say, 200 millimeters in all three directions, the size of your block is going up as a cube function, and but the parts you're saving are only going up as a linear or square function. So really, to break that barrier, you need a three-dimensional way of manufacturing, and that's what additive really provides. Casting provides it to some extent. But casting has lots of other limitations not in terms of capability, but in terms of cost and in terms of, I will say, delivered discontinuity content that makes AM a better candidate for those parts.
Now, considering AM as being a better candidate for these parts, my next question is for Sagar. To your knowledge, what is the general material availability for production and laser powder bed fusion across alloys, and specifically, what is the landscape for high-strength aluminum alloys in general in terms of processability for laser powder bed fusion?
Oh, yes. So I can speak mostly through the past 4 years of my PhD, where I think, especially towards the start of my PhD, past couple of years, let's say, the trend seemed to be mostly the heritage alloys used commonly in welding or casting, and especially they were for good reasons, because the general perspective is that if a material welds well, it will print well, and more often than not it turns out all right, but it becomes an issue, let's say, when you're working with martensitic materials, where you could get away with a weld line but you could not get away with a million weld lines stacked together. Then you cause issues like residual stresses and cracking in additive manufacturing, particularly laser powder bed or laser powder bed fusion. But now we increasingly see trends of moving, not exactly moving away, but at least having better options to replace heritage alloys for given applications. So we see that in nickel-based super alloys to deal with solidification cracking issues, as well as high-strength aluminum alloys. As an example, we have Scalmalloy, which is meant to address some of the limitations of the challenges, some of the challenges associated with conventional high-strength aluminum alloys.
Fantastic. So now knowing that there's quite a bit of potential in terms of product design, as well as potential for adoption of materials in laser powder bed fusion, and we know that laser powder bed fusion is among one of the more popular metal AM technologies, let's take a deeper technical dive into the laser powder bed fusion process and the methodologies for parameter development. And specifically, the next video will highlight process parameter optimization approaches adopted and further refined at the MSAM lab by Sagar for a particular challenging class of materials, such as high reflectivity alloys. So before we play the next video, I'll ask our panelists to maybe turn off the video so we can actually get a bit more bandwidth and hopefully successfully play our next technical video. So let's.
Metal vaporization-related defects are one of the biggest challenges in the printing of aluminum alloys, for which the potential to use defocused laser beams permitted in systems such as the Renishaw AM400 are useful. Aluminum alloys, similar to copper alloys, belong to a notorious class of materials whose absorptivity characteristics differ significantly when compared to conventional materials used in laser powder bed fusion, such as titanium, ferrous, and nickel-based alloys. The very low absorptivity of aluminum at lower energy inputs in conduction mode takes a sudden shift to high values once surface vaporization initiates. This peculiar behavior of aluminum is related to the increased number of laser ray reflections inside the vapor capillary created soon after surface vaporization. This behavior also makes aluminum more sensitive to keyhole defects, even at shallow melt pool depths. Our goal was to develop process parameters for Scalmalloy in 2 weeks or less. The approach we chose was based on physics-based modeling theory. Our previous work in developing processing maps guided the prediction of the experimental boundaries of conduction, transition, and keyhole melting modes. This work has been validated with data sets from numerous aluminum, titanium, ferrous, and nickel alloys. The processing maps help us analyze the physical origins of a given defect and guide us quickly towards a set of ideal processing parameters for a given alloy. This work has previously guided us towards the use of defocused laser beams for AL-SI10MG, leading to a uniform conduction mode microstructure. We used our prior knowledge with this alloy as a starting point for generating a process map for Scalmalloy. Our goal was to optimize microstructure, porosity, surface roughness, buildability, compression performance, and tensile performance. These evaluation criteria were geared towards addressing sustainment of traditionally manufactured 7000 series aluminum alloys, which are not printable using laser powder bed fusion. We tackled this with the combination of process diagrams, melt pool simulations, beam path planning, and X-ray commuted tomography to address the issue of porosity in Scalmalloy. We were able to complete the entire chain of process parameter development, printing, and testing components within a week. We wanted to prove to ourselves that fast process parameter development is possible and also enter in the USAF Manufacturing Olympics. The processing diagrams helped us narrow into stable conduction mode process parameters for Scalmalloy within 2 prints, wherein we were able to achieve densities of over 99.98%. When it comes to surface roughness, however, the excessive vaporization in the keyhole mode had been shown to be beneficial to obtain an improved surface finish, which was used for printing the final component.
But really, it is a challenging task to develop process parameters for laser powder bed fusion, and our quick turnaround for process parameter development at MSAM, which was stated to be less than 2 weeks, was really not by chance, and rather this was built upon prior experience with high reflectivity alloys. As we learned, we can transfer knowledge from prior processing experience with these types of materials. And also, I would like to remind our audience to type some of the questions in the chat, and I'll do my best to address them and post them to the panelists, either now or at the end of the session. So aligned with potentially what would have been, some really interesting videos or visuals, maybe Sagar can explain a little bit more and reenact some of the videos there by describing why is it challenging to print high reflectivity alloys in laser powder bed fusion. What are these high reflectivity alloys?
Sure. So hi, yeah, I wish the video hopefully had some of the observations on the differences between absorptivities for aluminum and even copper alloys compared to conventional alloys. So based on the current material classes we have available for laser powder bed fusion in particular, we can classify them into high reflectivity and low reflectivity alloys. And these high reflectivity alloys are such that but while you are still in the melting phase of laser powder bed fusion, let's say, the material by itself is not able to absorb as much of the laser energy input. So with aluminum alloys, let's say, when you are just in the melting phase, which is what we call the conduction mode, your absorptivities for aluminum alloys are close to 15% only. And for copper alloys, we expect it to actually go down as much as maybe 5% with the wavelength of the laser beams that we work with. I must also mention that I'm assuming that the conventional laser beam wavelengths that we have on the machines is what we are considering for purposes of this talk. But as soon as you have vaporization that initiates, it suddenly takes a dramatic turn, wherein from as low as 15%, it could go easily above 40%, and up to 70% has been observed in literature for aluminum alloys, the laser energy absorption. So this higher absorption is beneficial for some purposes, but it also makes these materials very challenging because it's really easy for you to get defects and porosity in aluminum alloys when compared to titanium or other alloys.
So when you go from undermelt to conduction to keyhole, what type of defects do you expect for the benefit of the audience, as the video was a bit lagged? Can you describe what happens at the material level?
Sure. So as soon as you initiate vaporization in aluminum alloys in particular, the amount of reflections that the laser beam, because the laser is like a beam of light, is able to undergo inside the aluminum is a lot. Like, I mean, it's difficult to give numbers to it, but it's just a lot more reflections of the laser beam once you have a vaporized portion of your material, because the vaporized portion itself is almost like a hole. So you now drill the hole into the material. So the laser beam has so many more pathways that it can interact with the material and thereby, give more of its energy into the material as opposed to being lost somewhere else. And this is what makes, but this is what also causes porosity, because when you drill the hole to be too deep or let's say either too deep or else your hole is very fluctuating. So it goes from too deep to too narrow to nothing. Those fluctuations are pretty common in laser powder bed fusion, which high-speed X-ray imaging has shown. And this is the major cause of porosities. Like you get spherical pores called keyhole pores. But on the other scale, when you're in the melting domain, if you don't melt enough of the material, then also you could have something like undermelting, where you have unfused powder particles causing lack of fusion defects. So keyhole and lack of fusion defects are two of the most common defects we observe in aluminum alloys.
So now that you've described a little bit of what you don't want to have in your product, for instance, porous defects, what is the typical workflow for process parameter optimization? Can you speak to that? And then again, stress why is it challenging specifically for high reflectivity alloys to achieve process parameter optimization?
Sure. So based on our experience with aluminum alloys for two different machines at our lab, one is the Renishaw system, which has a beam spot diameter of 70 microns, and one is the EOS, which has about 80 but could go to 100 microns. We decide how are we going to tackle process parameter development based on the beam spot diameter that we are working with, because based on a very thorough literature review by one of our master's students, Lisa, whose work was the inspiration of most of my interest in aluminum alloys, we were able to observe that conduction mode melting, which means like absence of vaporization, was just not reported for beam spot diameters below 100 microns from everything that we looked in literature from multiple PhD theses. And this is why whenever we are working with such systems, I decide to intentionally defocus the beam to a position above the build plate. So the laser beam spot diameter is the main variable that I like to work with for aluminum alloys. And that is the quickest way for us to obtain conduction mode parts, wherein your vaporization is assumed to be no vaporization. So that's how we were able to tackle Scalmalloy, and that's how I would go. But if you have the time to even further optimize, and if you want tailoring of microstructure, there are possibilities of obtaining near fully dense parts in the transition or keyhole modes as well, but it just needs more simulations and a lot more design of experiments to get you there.
And how long does this optimization typically take? I mean, the 2 weeks was kind of unusual because you had all this prior knowledge with other alloys. But typically, how long do you think it takes to do a process parameter optimization cycle, at least in the academic setting?
Yes, actually, so I can maybe give an example of copper alloys, let's say, which is where we not had any experience. So if I don't have any experience on a given alloy, I'd probably tackle it with like beginning. I would go to literature and plot all the points on our processing diagrams and at least start with one design of experiment for CT scanning coupons, which thanks to your and Professor Toysakani's vision, we have a very established workflow in our lab that we can go from printing to CT scanning within a day and have the analysis within 2 days. So that itself kickstarts process parameter development for any material. And then wherever in the CT scans of the given first experiment we see interest, that's where I would then like to go and observe the melt pools and the porosity shapes to confirm that is this what my processing diagram predicted, and is this the reality what we are expecting or not. And I think then a maximum of 2 more design of experiments should be enough. So I really do not anticipate more than 3 design of experiments for any material. Other than that, it will just be on the complexity of your shape. So if you have to print lattices and highly complex lattices, that adds more challenges because of overhanging features and other complexities.
Thank you so much, Sagar. My questions, the next few questions are for Kevin and John. Really, why is it so important to go through this optimization step, specifically for density and surface quality, in light of where these types of materials are applied in industry?
Yeah. So primarily, right, when someone's selecting a high-strength aluminum alloy, it's because they have a demanding structural application. And oftentimes that structural application includes not just static loading, but fatigue loading. And if you have material with pores in it or a poor surface finish, you can very quickly take all the benefits of design for AM and kill it with a huge fatigue knockdown due to surface finish or discontinuities. So generative design just does not work out for you because you wind up with poor properties.
And specifically, in looking at comparing the the target of 99.9 and above, or 99.99 and above density for laser powder bed fusion, how does that compare to conventional manufacturing for these types of alloys? Are we in the same range, or is it a little bit far off?
It's very close. When you get to that high of a density, really density is not so much the number you're interested in anymore. It's maximum discontinuity size and how frequent they are. So you go from percent to microns, and your typical wrought materials are generally free of this. You will have a random rogue, maybe an inclusion or something like that in it, but that's about it.
And I think that this is kind of where the other aspects of manufacturing come in, and so the system set up today, knowing what the defect structure is in these materials, it's well quantified, and so we have metrics, if you will, for things like what is a minimum detectable flaw size in a material, and then aerospace, being a conservative industry, assumes that defect is present and designs for the presence of that. So, we've seen with additive, I think, Ryan DeHoff and some other people at Oak Ridge have done some interesting work where they're looking at the defect structures in additive, but how it orients itself and aligns makes a difference. So if you have 0.001% pores, but they're all clustered around the same thing, that's different than having them dispersed, in a linear orientation. So, it's additive makes things a bit more complicated, but at the end of the day, we're used to complex.
Now, going beyond defects and looking at material properties a little bit, because additive, for instance, can really influence the microstructure locally within a component. Maybe John, can you speak to what are some of the most important material properties to target for the aerospace sector?
Well, I mean, stiffness is typically the number one thing for most people, but that being a physical property, the specific stiffness of aluminum silicon 10 and a 7000 series are approximately the same. Where Scalmalloy comes in is around the strength, and the 7000 series have higher strength. So on a specific strength basis, they're there. And to Kevin's point, this tends to scale with the fatigue resistance of the material also. This is where the material science comes in, because today, as a materials guy, I look at what we're doing in additive and we just dump infinite energy into it to try to get it to melt. But the absorptivity of the material is actually what we're trying to overcome. And so maybe not using shiny, metallic balls that reflect light very, very well isn't the best approach. And how much of that problem goes away if we understand the physics of the coupling, and that doesn't create more material science problems because we've boiled off the light elements, et cetera. So there's definitely a material science problem that I think the industry's, I'll say, largely waved its hand at, and we have some interesting people like HRL and Elementum 3D who won the gold medal. We give them their props. They have very novel approaches to getting the strength back, but it's perhaps not the alloy that you started with. So it does give you the strength. It's just a little bit different.
So now, as John hinted, really in laser powder bed fusion, the laser material interaction is a micro welding process, and your material undergoes melting, vaporization, ejection, and cyclic thermal heating and cooling. So again, with this type of manufacturing approach, you're influencing the microstructure and material properties of the final component, and how much you can recover in terms of strength via post-process and heat treatments is always challenging to balance. Now, in laser powder bed fusion, we have more than 100 process parameters that can be tuned during manufacturing, and these parameters are also sensitive to the design geometries being printed and can result in part failure if not selected properly. In our last video, let's take a brief look at some of the testing that was done for Scalmalloy, followed by a quick discussion on what type of performance testing is expected in industry to qualify components.
The printed Scalmalloy components were then subjected to rigorous testing at the U.S. Air Force facility in Ohio during the Advanced Manufacturing Olympics, which included metallography, tensile testing, surface roughness testing, X-ray computed tomography, and compression performance. Out of 10 finalists, we were awarded a silver medal for our work with Scalmalloy in the Material Hurdles Challenge. We hope that this work will help expand the material universe for the printing of end-use components for the aviation sector.
So thank you so much, Cynthia, for playing the video. And now our components were tested as part of a competition with further work happening in the background for further characterization of this material system as a collaboration between TBGA and MSAM. Now, some of our tests are more typical for the academic performance characterization and reporting, but what happens in industry may be quite different. So my first question is for Kevin. What type of testing and to what level of rigor is done for qualifying aerospace components?
So this is becoming more better defined across the industry, but the aerospace uses very much a building block approach. You start off with process and parameter development, small coupons, tensile coupons. And then you move on to component and machine, which is often still tensile coupons, and then you'll finish up in the end with part qualification and system certification with that. And that depending on the approach you use, that can range from hundreds to thousands of coupon tests. It can range from looking at 3 or 4 properties to looking at 1 or 2 followed by a component test. And it can also entail analyses, subtests. For example, if you want to use a part with the as-built surface finish and there's a fatigue environment, developing what those knockdowns are for the fatigue. If you're interested in certain size defect type being below that, you can have what's called effects of defects testing. So it's a real range, and the industry, I would say, in the last 5 years has made extensive progress, not only in finally deciding what it needs, but also more and more standards are starting to come out in a very common language across the aerospace.
Now, considering the rigor against which laser powder bed fusion components need to be tested at, as well as where some of these components are going in the aerospace sector, what do you think are the gaps in terms of industrialization of components coming off of laser powder bed fusion processes? And this is a question really for all panelists on the line.
I'll let John answer that.
We were going to stare off on that one. So there's numerous things. I mean, it is in production today. It's on demanding aircraft. It's on Mars. So I think the Pathfinders show that it can be done, and it can be done safely. The quality components there's questions. There's a lot of levers, as you pointed out, with all the different variables that are out there. And there's only so far you can get with what we call fixed processes. That's a very tedious way of doing things. It works, but it's not the way you'd want to do it every time. So I think a lot of the work that's going on, at the universities and elsewhere, we're looking at more process maps, where we kind of know where we exist in space, as opposed to everything being sort of, one-dimensional. You don't know whether you're on the edge of badness or not. So it's all getting better, and I think at the maybe 20 years from now, when we look back at this, we're able to collect a lot more information about how we produce things than we ever have been able to do. It's always been an artifact of paperwork, except now we actually can observe, we can have actual data, video data, and, whatever form that digital information exists, it could be kept, in perpetuity, really. So I think there's always reasons you can keep it out of production, but if you are affordable, if you show reproducibility, people will figure out how to use it.
So let's say that through efforts from really smart people, one of them, for instance, being Sagar here in the room, we figure out all the kinks of producing parts via laser powder bed fusion using high strength aluminum alloys. What is the supply chain for these alloys at the moment, and are there any opportunities emerging? Are there any bottlenecks or kind of future vision for these types of alloys, specifically for additive manufacturing?
I think just because scandium's been a minor infatuation of mine ever since I was, probably a grad student, Scalmalloy and the scandium-containing aluminum alloys have a unique kind of techno-economic situation in that during the Cold War, Russia was producing scandium-containing aluminum alloys that were in production on MiG fighters, but they also had most of the world's stockpile of aluminum scandium containing materials. And I will say, so scandium has enjoyed this reputation as being exotic, rare, in all the wrong places. And, for some for good reasons and maybe not. But, I think what we're seeing now is that there's more commercial sources of scandium becoming available, partly because it's also good for things like fuel cells. It's not really a rare material. It's not a rare element. Places like Australia are opening up mines that are friendly democracies. And so I think that this will improve, but it's important to know, because it's actually one of the questions in here, which was, why has it not enjoyed more success? And it's all of these factors kind of come together and make it, it's not a competitive, there's not a lot of material producers making a scandium material. Airbus owns the patent on this material. We should, credit John Meyer at AP Works for getting us the sample materials. But, I've been colleagues with John for many years, and I think we both enjoy the promise of scandium, but also appreciate the challenges of the economics of scandium. And I'm optimistic about it. But then we also need smart people like Sagar who can turn it around in 2 weeks after never having seen it before.
And we didn't sleep for those 2 weeks, so maybe that's an unrealistic goal in a real environment. So my next question is for Sagar. What were some of the most interesting scientific learnings that you discovered during this program?
I think it was our first time working with like a high strength aluminum alloy in all so forth. We had only worked with ALSite and MG. So it was really nice. Like I think it was just the first time I met Dr. Slattery. He already had recommendations and connected us to multiple sources for Scalmalloy, as well as another alloy that we were considering. And I had not really had a good understanding of what are the challenges with the conventional high strength aluminum alloys. So that was very good to learn from a scientific standpoint, that not in all cases, but in almost all cases, that the simple reason why they are not so suitable for additive manufacturing, high strength aluminum alloys and some of the nickel alloys, is the difference between the solidus and liquidus temperature. Like which means that if you have too many alloying elements, and especially alloying elements which are not as compatible, a portion of your
Oh, we've lost Sagar just when he was getting to the most important part. Oh,
but and your liquid system, by the way, liquid is the point that all of your material is now in the liquid stage.
We lost you, Sagar, about 10 seconds ago.
Hello. Okay. But yeah, I was saying that just the difference between the solidus and liquidus temperatures, which is basically when the material starts melting and when the material has completely melted, is one of the biggest factors influencing whether or not it will crack during solidification. And this was quite an interesting journey for me to learn, and I think that's gotten me a lot more excited to work on such challenging materials, or how do we counter that, maybe from toolpath algorithms with our simulation attempts.
Now, my last question for Kevin is for Kevin and John, really. When you consider the complexities of going from powder to part, those competencies to achieve, quality parts and sound parts, those technical competencies may not reside all within one organization. They may be essentially leveraged across industry partners as well as academic partners. How do you envision kind of a good path for someone who's really trying to learn about additive processes or maybe dive into additive processes to be able to leverage these partnerships such that it's not necessarily a daunting task of achieving all of this in-house? So I don't know if you have any ideas on that end, because really this was one example where we really never met. We were never in the same room. Yet we were able to execute a project with remote sites for testing, production, characterization, and so on.
Yeah, so I think, although we didn't meet during the exercise, we had met previously. So we had a bit of a working trust, if you will, going into it. And it was, relatively easy from but I didn't really have to do much. I was answer some questions occasionally. Sagar was the one who wasn't sleeping for 2 weeks straight, but next time, maybe it's only 3 weeks. I think that, certainly there's avenues to get training now, as Mihaela, you and I on our SME advisory capacity have we do career sessions for people. I've got one coming up here shortly where people can get information. This next one's specifically on design and applications engineers for additive. So there's a lot of more resources coming online. There's training that's available. We offer training. Other people offer training. And so there's no shortage of information. It's really a kind of knowing what your angle is on the field, and that can be a challenge as well. So I think there's a lot of, unfortunately there's a lot of information out there, but the good news is there's a lot of information out there.
And maybe in Kevin's perspective, because you really went from powder to product all within one organization. How is that experience versus kind of distributing the outsourcing competencies to pull together a program?
Yeah, that was, the fact that everything could be done in one place at MSAM, having a multidisciplinary research center where you can do all this is extremely helpful, right? You don't have to, because I've worked other programs where now I send my, I have to get a contract in place with the parts builder, so they make the parts. I got to get a contract with the powder person. I have to get a contract with the NDT house, and before long, right, you've got 12 weeks of paperwork to do 2 weeks worth of work, and so centers like yours really helps. I was also going to jokingly say, since no money changed hands, right, we didn't have to go through the contracting loop with MSAM.
Hopefully not months of tears for that one.
In intellectual property work, but the more capable centers like MSAM and some of the ones that I've worked with, on this side of the border, really helps with that. That you can get everything done in one place, especially when you have only a semi-defined statement of work. When you go to industry, you got to give them a very defined statement of work and say, make this many builds, this many coupons, do this many tests, and that really slows down your learning loop. So having a place that can do lots of things, can get that 95% answer and turn the loop in 2 weeks is very useful.
Yeah.
Well,
I think I just
go
was
ahead,
going to add 2 cents there. I mean, I think that this is where universities, a lot of times, and to some extent, national labs get a little bit of a bad reputation as being, slow or difficult to work with. Well, I mean, they are what they are. It's a little bit like being surprised the ocean is salty, and so but it also is very buoyant. So it can do fascinating things for you. You just need to know when to use it versus something else. And speed is relative. So if you're an F1 driver, your definition of speed and my definition of speed are very different. So I think knowing when to engage a university and at what level is important, to Kevin's point.
And really, the good news is that there's a wealth of academics who are tackling a lot of really challenging problems in metal AM, and again, globally. So there's kind of a boom in terms of interest as well as efforts. And really, because of time constraints, I really hope that today's event provided a glimpse of the realities of going from powder to part in laser powder bed fusion. As well as inspired you to look further into additive manufacturing technology adoption for high-strength aluminum alloys and other metals in general. And we hope that you are also inspired to connect and engage with knowledgeable partners, either industrial or academic, to really de-risk some of your AM R&D and to learn more about these technologies. And I would like to thank each and every one of our panelists for sharing their perspectives today. I would also like to thank the hardworking team in the background, Cynthia Rogers at TBGA, Mark Kirby and Maria Peskova at MSAM for taking the lead to put together the story and the video behind today's event, or the videos behind today's event. And we'll share the links for the videos. They're really great. Lots of effort went into those, and I hope those will shed some light into further insights for laser powder bed fusion. And a final thanks to our panelists, really, who contributed to technical content to make all of this happen. And last but not least, I would like to thank you, our audience, for being part of today's event. If you have further questions or if you would like to connect, please join us at the roundtable discussions. We will be around for another 30 minutes or so to engage with you. And stay on the line as we close off this event and move into the kind of table discussion settings. So we hope to see you there. Thank you.